In this episode, we're going to bring a lot of the ideas you have been building together and apply them to one of the most common places sensitive data ends up in the cloud: storage services. Cloud storage is powerful because it is easy to use, flexible, and scalable, which is exactly why it becomes a central dependency for applications, backups, analytics, and everyday file sharing. That ease is also what makes it dangerous when security is treated as an afterthought, because one careless setting or one overly broad permission can expose huge amounts of data without breaking anything operationally. Many real incidents are not advanced hacks. They are the result of storage being configured in a way that relied on hope, such as hoping nobody guessed a URL, hoping a default stayed safe, or hoping a temporary exception would be removed later. Securing storage by design means you decide in advance how storage should be created, how it should be accessed, how it should be monitored, and how it should be audited, and then you make those decisions hard to bypass. The goal is to build storage security that remains reliable even when teams are busy, systems are changing, and attackers are looking for the easiest path. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful first step is to define what cloud storage services are in a way that highlights why they matter for security. Storage services include object storage for large numbers of files and data objects, file-style storage that feels like shared folders, and block-style storage attached to compute resources. Even if you do not memorize categories, the core idea is that storage is where data rests, accumulates, and multiplies, and it often contains the most valuable information in an environment. Storage is also the place where many other services write their outputs, such as logs, backups, exports, and analytics datasets, which means storage becomes the meeting point of many workflows. That makes storage a high-value target because compromising storage can yield credentials, customer data, business records, and operational intelligence in one sweep. It also makes storage a frequent source of accidental exposure because different teams interact with it for different purposes, sometimes without a shared understanding of sensitivity. If you want cloud security to be real, storage security must be intentional and systematic, because storage is where mistakes become big. Designing storage security starts with a classification mindset, because not all stored data has the same sensitivity and not all storage locations should have the same access pattern. Some storage is public by nature, like a website asset repository, while other storage should be tightly private, like customer records or security logs. The danger comes when teams treat all storage like it might be useful to share, or when they treat private storage like it is harmless because it is only for internal use. A design approach defines default privacy for sensitive storage and defines clear exceptions for truly public content, with explicit justification and controls. This is where beginners often get tripped up, because cloud storage can be shared easily, and the user interfaces often make sharing feel normal. A mature design flips that by making private the baseline and making public access a deliberate, rare decision that is visible and reviewable. When classification drives design, you reduce the chance that a sensitive dataset is accidentally treated like a public asset. Access control is the heart of storage security, because encryption at rest does not prevent an authorized identity from reading data through normal service access. Storage access decisions should follow least privilege, meaning each identity gets the minimum access needed for its job, and those permissions should be scoped to the smallest set of resources possible. For example, an application that needs to read one set of objects should not be able to read every object in the environment. A team member who needs to upload data should not automatically be able to delete it, and a user who needs to browse reports should not automatically be able to change access policies. Cloud storage is often accessed by automation identities as well as humans, so access design must consider both and avoid reusing broad human credentials for machine tasks. The goal is to make access precise, explainable, and auditable, because broad access makes both misuse and mistakes harder to contain. A design that treats storage access as a central security boundary is far stronger than a design that treats storage like a shared drive. One of the most important design choices is preventing unintended public exposure, because public exposure is a common root cause of cloud data incidents. Storage services often provide ways to share data publicly, and sometimes that is necessary, but the safe approach is to make public sharing difficult to do accidentally and easy to detect when it happens. This means designing with explicit rules that distinguish public content repositories from private sensitive repositories, rather than mixing both in the same place. It also means limiting who can change access policies, because policy changes can instantly expose large datasets. Another important aspect is understanding that public exposure is not only about a setting that says public, but about the effective access path, meaning whether an unauthenticated or unintended user can retrieve the content. Attackers do not care whether the exposure was intended, they care that it exists. When you design storage to minimize exposure paths and to make exposure changes rare and visible, you stop relying on hope. Network boundaries can also support storage security, but they must be treated as supporting controls rather than as the primary control. In cloud environments, relying solely on network location is risky because identities and services can access storage from many places, and network boundaries can drift or be bypassed through misconfigurations. Still, a strong design often uses network restrictions to reduce exposure, such as limiting access to storage from approved environments or reducing access paths from the public internet where possible. The key is that network restrictions should reinforce identity controls, not replace them, because identity remains the primary perimeter in most cloud architectures. When network boundaries and identity boundaries align, attackers have fewer options because they need both a valid identity and the right access path. When network boundaries are loose or inconsistent, identity misuse becomes easier because the attacker can use stolen credentials from anywhere. A design approach treats network restrictions as an additional layer that reduces attacker opportunity and reduces accidental exposure. Encryption is an essential part of storage security, but the design mindset treats encryption as a baseline requirement plus key governance, not as a comforting label. Storage should be encrypted at rest with sane defaults so that new storage resources are protected automatically, and that protection should extend to backups, replicas, and other copies where the same data might appear. Key management matters because encryption is only as strong as key usage boundaries, so sensitive storage should use keys with clear ownership and restricted decrypt capability. This is where Key Management System, KMS, design connects directly to storage design, because storage encryption often depends on the KMS for key policy and audit evidence. A design approach ensures that the identities that can access storage do not automatically have broad key administration rights, and that key usage is logged and reviewable. Encryption should also be validated so enabled means coverage is real, including across lifecycle artifacts like backups. When encryption is designed and verified, it becomes a real barrier rather than a symbol. Logging and monitoring are what transform storage security from a static configuration into a living system that can detect misuse and support investigation. Storage activity should be visible enough that you can answer questions like who accessed data, what was accessed, and whether access patterns changed in suspicious ways. This matters because many storage incidents are discovered late, and without logs you cannot confidently determine scope or timing. Monitoring should also focus on high-impact events, such as changes to access policies, changes to encryption settings, large-scale data reads, and large-scale data deletions. A design approach ensures that the logs needed for storage accountability are enabled, retained, and protected from tampering, especially by identities that could misuse storage. It also encourages defining normal storage access patterns so anomalies stand out, because unusual behavior is easier to detect when baseline behavior is predictable. When monitoring is treated as part of storage design, storage becomes safer because misuse becomes harder to hide. Secure storage design also includes lifecycle thinking, because storage is where data often accumulates far longer than intended. Retention and deletion decisions are security decisions, because keeping sensitive data longer than necessary increases the amount of data that can be exposed if access is misused. A design approach defines retention expectations for different data types, ensures that old data is disposed of safely, and ensures that backups and archives follow the same expectations. It also means controlling replication and copying, because copies can spread sensitive data into places with weaker controls. For example, copying data into an analytics environment might be useful, but it must be done with clear boundaries and strong access control, or it becomes a leak path. Lifecycle design also supports legal and audit needs because it creates evidence that data handling is intentional rather than accidental. When storage retention and disposal are planned, security improves because the attack surface is smaller and less cluttered. Another design concept that matters is configuration consistency, because storage security often fails through drift and exceptions rather than through initial configuration. A storage environment can start secure, then slowly become insecure as teams create new buckets or shares with slightly different rules. Drift happens when secure defaults are not enforced everywhere or when multiple provisioning methods produce inconsistent results. Exceptions happen when teams temporarily weaken access controls to meet a deadline and then forget to restore them. A design approach includes regular measurement of storage configurations, access rules, and encryption coverage so drift is detected quickly. It also includes governing exceptions so they are documented, limited in scope, and reviewed, rather than informal shortcuts that become permanent. Consistency is not about being rigid for its own sake. It is about making security outcomes predictable and verifiable. When storage security is consistent, both audits and operations become easier because people know what to expect. Storage design must also account for human behavior, because end users often interact with storage through file sharing, uploads, and collaboration workflows. If secure sharing is too difficult, users will find workarounds, such as copying data to personal accounts or using unapproved sharing mechanisms. A design that fits reality provides clear, approved ways to share data with appropriate controls, such as time-limited access, scope permissions, and visibility into who has access. It also includes user education at the right level, explaining why sensitive data should not be placed in public locations and how to request approved access for partners or contractors. The goal is not to punish users, but to make secure behavior natural and convenient, because convenience is a major driver of risk in storage security. When storage workflows are designed to support real collaboration needs, teams are less likely to create risky shortcuts. This is another reason the title emphasizes design rather than hope, because hope assumes perfect behavior, while design anticipates human needs. Auditing and evidence are what makes storage security defensible, because storage is often the first place auditors look when assessing data protection claims. Evidence includes records of encryption coverage, access control configurations, policy change history, and logs that show who accessed what. It also includes proof that the organization reviews access periodically and that it responds when storage is misconfigured or exposed. A strong design makes evidence collection easy because it standardizes how storage is configured and how changes are tracked. When evidence is available, incident response becomes more effective because responders can determine whether data was accessed and whether exposure was likely. Legal scrutiny also becomes more manageable because the organization can demonstrate a consistent approach to protecting sensitive information. Without evidence, even strong configurations become hard to defend because you cannot prove what was true at the relevant time. Designing storage security with evidence in mind is therefore not bureaucracy. It is part of making security real. Beginner misunderstandings often show up clearly in storage security, and addressing them helps you build a more realistic posture. One misunderstanding is believing that storage is safe because it is in the cloud, when in reality cloud storage is accessible through identities and policies that you control, for better or worse. Another misunderstanding is believing that encryption alone prevents leaks, when in reality access control and key boundaries determine who can see plaintext. A third misunderstanding is assuming that public access is obvious and will be noticed immediately, when in reality exposures can persist quietly if monitoring is weak. Beginners also sometimes assume that storage is only used for files, overlooking that logs, backups, and exports are also stored data and can contain highly sensitive content. Finally, many beginners underestimate drift and exception creep, thinking that once a bucket is configured securely it stays that way, when in reality changes happen constantly. The secure approach replaces those misunderstandings with design choices that enforce safe defaults, tight access, strong monitoring, and consistent verification. By now, the big picture should feel coherent. Securing cloud storage services by design means treating storage as a high-value security boundary and building guardrails that remain strong over time. You define what data is sensitive and make private access the default, with public exposure treated as a rare, controlled exception. You design precise access control for both humans and automation identities, and you limit who can change storage policies so exposure cannot happen casually. You use network restrictions as supporting controls, and you apply encryption as a baseline, with Key Management System, KMS, boundaries that make decryption power controlled and auditable. You build logging and monitoring so storage use is visible and misuse is detectable, and you manage data lifecycle so retention and copying do not silently expand risk. You measure configuration drift and govern exceptions so the environment remains consistent and verifiable rather than drifting into insecurity. You design sharing workflows that fit human reality so users can collaborate safely without resorting to risky shortcuts. When you do all of that, storage security becomes something you can trust and prove, not something you merely hope is fine. And that is exactly the kind of security posture cloud environments demand.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.